When we look at the universe today, we know with an extraordinary amount of scientific certainty that it wasn't simply created as is, but evolved to its present configuration over billions of years of cosmic history. We can use what we see today, both nearby and at great distances, to extrapolate what the universe was like a long time ago, and to understand how it came to be the way it is now. When we think about our cosmic origins, then, it's only human to ask the most fundamental of all possible questions. Where did this all come from? It's been more than half a century since the first robust and unique predictions of the Big Bang were confirmed, leading to our modern picture of a universe that began from a hot, dense state some 13.8 billion years ago. But in our quest for the beginning, we know already that time couldn't have started with the Big Bang. In fact, it might not have had a beginning at all. Time does not exist. We invented it. Albert Einstein. This concept, backed by British physicist Roger Penrose, raises questions about the Big Bang along with alternative cosmic origin theories.
And then people got accustomed to the Big Bang being there. Or not just being there, you see, I'm claiming it is there, but it's not the beginning.
Join us as we dig deep into one of the age-old questions about our vast universe. Was the Big Bang really the beginning of time? Or did the universe exist before then? Such a question seemed almost blasphemous only 3 decades ago. Most cosmologists insisted that it simply made no sense, that to contemplate a time before the Big Bang was like asking for directions to a place north of the North Pole. However, developments in theoretical physics have changed their perspective. As a result, the pre-Bang universe has become the latest frontier of modern cosmology. But note that whenever we think about anything, we apply our very human logic to it. If we want to know where the Big Bang came from, we describe it in the best terms we can, and then theorize about what could have caused it, and set it up. We look for evidence to help us understand the Big Bang's beginnings. After all, that's where everything comes from the process that gave it its start. But this assumes something that may not be true about our universe, that it actually had a beginning. For a long time, scientifically, we didn't know whether this was true or not. Did the universe have a beginning, or a time before which nothing existed? Or did the universe exist for an eternity, like an infinite line extending in both directions? Or, quite possibly, is our universe cyclic like the circumference of a circle, where it repeats over and over indefinitely? For a time, there were multiple competing ideas which were all consistent with the observations we had. First, an expanding universe could have originated from a singular point, an event in space-time, where all of space and time emerged from a singularity. Second, the universe could be expanding today because it was contracting in the past, and will contract again in the future, presenting an oscillating solution. Finally, the expanding universe could have been an eternal state, where space is expanding now and always had been and always would be, where new matter is continuously created to keep the density constant. These 3 examples represent the 3 major options. The universe had a singular beginning, the universe is cyclical in nature, or the universe has always existed. In the 1960s, however, a low level of microwave radiation was found everywhere across the sky, changing the story forever. This radiation wasn't just the same magnitude everywhere, but also the same in all directions. At just a few degrees above absolute zero, it was consistent with the universe emerging from an earlier, hot, dense state, and cooling as it expanded. As improved technology and novel techniques led to better data, we learned that the spectrum of this radiation had a particular shape, that of a near-perfect blackbody. A blackbody is what you get if you have a perfect absorber of radiation heated up to a certain specific temperature. If the universe expands and cools without changing its entropy, something that starts off with a blackbody spectrum will remain a blackbody even as it cools. This radiation was not only consistent with being the leftover glow from the Big Bang, but was inconsistent with alternatives like tired light or reflected starlight. According to the Big Bang, the universe was hotter, denser, more uniform, and smaller in the past. It only has the properties we see today because it's been expanding, cooling, and experiencing the influence of gravitation for so long. Because the wavelength of radiation stretches as the universe expands, a smaller universe should have had radiation with shorter wavelengths, meaning it had higher energies and greater temperatures. Billions of years ago, it was once so hot that even neutral atoms couldn't form without being blasted apart. Even earlier than that, today's microwave radiation were so energetic that they dominated over matter as far as the universe's energy content was concerned. At even earlier times, atomic nuclei were instantly blasted apart, and at still earlier ones, we couldn't even create stable protons and neutrons. If we extrapolate all the way back to arbitrarily hot temperatures, small distances, and high densities, you'd intuit that this would truly equate to the beginning. If you were willing to run the clock backwards as far as you could, all of the space that makes up our visible universe today would be compressed down to a single point. Now, it's true that if you went to these extreme conditions, compressing all the matter and energy present in today's universe into a tiny enough volume of space, the laws of physics would break down. You could try to calculate various properties, but you'd only get nonsense for answers. This is what we describe as a singularity, a set of conditions where time and space have no meaning. At first glance, if you do the math, it appears that a singularity is inevitable, regardless of what dominates the universe's energy content. Singularities are where the law of gravitation governing the universe, Einstein's general relativity, yields nonsense for predictions. Relativity, remember, is the theory that describes space and time. But at singularities, both spatial and temporal dimensions cease to exist. Asking questions like, what came before this event where time began, is as nonsensical as asking, where am I if space no longer exists? Indeed, this is the argument that many make, including Paul Davies, when they claim that there can be no discussion of what occurred before the Big Bang. This is a tautology, of course, if you assert that the Big Bang is where time began. But as interesting as this argument is, we know that the Big Bang isn't where time began anymore. Ever since we've made modern, detailed measurements of the cosmos, we've learned that this extrapolation to a singularity must be wrong. In particular, the patterns and magnitudes of the fluctuations that we've discovered in the modern radiation left over from that early, hot, dense state teach us a number of important properties about our universe. They teach us how much matter was present in dark matter as well as normal matter, protons, neutrons, and electrons. They give us a measurement of the universe's spatial curvature, as well as the presence of dark energy and the effects of neutrinos. But they also tell us something vitally important that's often overlooked. They tell us whether there was a maximum temperature for the universe back in its earliest stages. According to the data from WMAP and Planck, the universe never achieved a temperature greater than about 10 to the power of 29 Kelvin. This number is enormous, but it's over 1,000 times smaller than the temperatures we'd need to equate to a singularity. The particular properties of the universe that are imprinted upon it from the earliest stages provide a window into the physical processes that took place at those times. Not only do they tell us that we cannot extrapolate the Big Bang all the way back to a singularity, but they tell us about the state that existed prior to and set up the hot Big Bang, a period of cosmic inflation. During inflation, there was a tremendous amount of energy inherent to space itself, causing the universe to expand both rapidly and relentlessly at an exponential rate. This period of inflation occurred prior to the hot Big Bang, set up the initial conditions that our universe began with, and left a series of unique imprints that we searched for and discovered after the theory had already predicted them. By any metric, inflation is a tremendous success, but this severely alters our conceptions of how the universe began. In an inflationary universe, no matter how far back you go, you never reach it, a singularity at a specific time. So, like many great discoveries in science, this leads to a slew of delightful new questions, including, was the inflationary state a constant one? We do not know whether the universe inflated at the same rate everywhere, or whether it inflated for long periods of time. If the universe inflated in ways that changed very quickly from one moment to the next, varying from location to location, it might still have the properties we observe it to have today. Did the inflationary state last forever, going backwards in time? Inflation certainly has the potential to be an eternal state. We believe in the regions where it doesn't end in a hot Big Bang. It continues eternally into the future. But could it have also been eternal to the past? With nothing forbidding it, we must consider the possibility. Is inflation connected to dark energy, which is also a form of exponential expansion? Although they're different in scale and magnitude, the early-stage cosmic inflation and the late-stage dark energy both give the same mathematical form for the universe's expansion. Are these two stages related, and will our future expansion increase in strength and rejuvenate our universe, like some sort of cosmic cycle? Observationally, we don't know the answer to any of these questions. The universe, as far as we can observe it, only contains information from the final 10 to the power of negative 33 seconds or so of inflation. Anything that occurred prior to that, which includes anything that would tell us how or if inflation began and what its duration was, gets wiped out as far as what's observable to us by the nature of inflation itself. Theoretically, we don't fare much better. The Borda-Guth-Vilenkin theorem tells us that all points in the universe, if you extrapolate back far enough, will merge together, and that inflation cannot describe a complete space-time. But that doesn't necessarily mean an inflating state couldn't have lasted forever. It could just as easily imply that our current rules of physics are incapable of describing these earliest stages accurately. Even though we can trace our cosmic history all the way back to the earliest stages of the hot Big Bang, that isn't enough to answer the question of how or if time began. Going even earlier, to the end stages of cosmic inflation, we can learn how the Big Bang was set up and began, but we have no observable information about what occurred prior to that. The final fraction of a second of inflation is where our knowledge ends. Thousands of years after we laid out the three major possibilities for how time began, as having always existed, as having begun a finite duration ago in the past, or as being a cyclical entity, we are no closer to a definitive answer. Whether time is finite, infinite, or cyclical is not a question that we have enough information within our observable universe to answer. Unless we figure out a new way to gain information about this deep, existential question, the answer may forever be beyond the limits of what is knowable. In short, time is one of those deeply stirring topics, but in some sense, it's the kind we tend to push aside and prefer to forget. After all, to think about time and how fast it passes leads quickly to thoughts about death. This is the essence of the human predicament. To have awareness of the passage of time, to know that our days on this planet and in this life are finite. Still, some of us do think about the nature of time, and physicists, far from being morbid folks, do that a lot. We tend to split time into three segments: past, present, and future. As everyone knows, past is what comes before the present, what was, while the future is what comes next, what will be. Even if this split seems obvious, it isn't. It's more of an operational definition, which, under further analysis, becomes quite nebulous. We need the present to define the past and the future. But what, exactly, is the present? Whatever is defined in time needs to have duration. We can look back at our lives and call that expanse of time the past. We can look forward and call what's to come the future. But what is the in-between demarcation point? The present is as thin as it can be. In fact, mathematically, we define the now as a single point in time. This point is an abstraction and, Being a point, it has no duration. Ergo, mathematically, the present is a point in time with no duration. The present doesn't exist, or at least it doesn't have duration in the mathematical definition of time. On the other hand, we do have a sense of the present. Our minds create the feeling of duration so that we can attribute reality to what we call the now. Time is, essentially, a measure of change. When all remains the same, time is unnecessary. That's why there is no time in paradise. No change, no time. But if we need to describe the motion of a car, or of the moon around the earth, or of a chemical reaction, or of a baby growing into a toddler, we need time. Near the end of the 17th century, Isaac Newton defined what we call absolute time, a time that just flows steadily like a stern river and is the same for all observers. That is, people or instruments making measurements of things moving about. Early in the 20th century, Albert Einstein argued that this notion of time is a crude approximation to what really goes on. Time and duration, he said, depend on the relative motion between observers. A famous example is the definition of simultaneity, when two or more events are said to happen at the very same time. Einstein explained that two events that happen simultaneously for an observer, A, happen at different times for an observer, B, in motion with respect to A. Inspired by the train station in front of his home in Bern, Einstein used trains to illustrate his revolutionary idea. Imagine A is standing by the station as a train goes by. When the train is exactly halfway through, two lightning strikes hit its front and back. Observer: A measures the time it takes for light from both strikes to get to her and concludes they arrived at the same time. They were simultaneous. However, observer B was inside the moving train. To him, the lightning strike that hit the front of the train arrived to him before the one hitting the back. The reason is simple, Einstein suggested. Since light travels at the same speed no matter what, and this was his revolutionary assumption, and the train is moving forward, the lighting hitting the front would have a shorter distance to travel and, hence, arrived at observer B before the lightning that hit the back, which had to catch up with the moving train. Now, for normal train speeds, the difference is ridiculously small. That is why we do not notice such things in ordinary life. And that is why Newton's approximation of absolute time, irrespective of the observer's motion, works for everyday stuff. But as speeds increase and approach the speed of light, the differences become noticeable. This effect has been measured countless times in the laboratory and in other experiments, confirming Einstein's special theory of relativity. Time and its perception is indeed quite subtle. Einstein didn't stop there. 10 years later, in 1915, he published his general theory of relativity, showing that once we include accelerated motions, we must rethink gravity and the nature of space and time altogether. In a spectacular display of intuition, Einstein realized that gravity mimics acceleration, like when you go up or down in a fast elevator and feel your weight change. He realized that to understand accelerated motion with a constant speed of light was equivalent to describing gravity as the bending of space and time. Very roughly, whenever there is a gravitational pull, it gets harder to move away from it. Even light is affected, not in its speed but in its wave properties, becoming stretched out as it tries to move away from a region with strong gravity, like near a star and, more dramatically, near a black hole. If you think of a light wave as a kind of clock, you can count how many wave crests pass by you per second, for example. You see that gravity decreases the number of crests going by. The stronger gravity is, the fewer crests you will count. This kind of reasoning applies to any sort of clock, and it translates into saying that gravity slows time down. So both in what we can call cognitive time, the subjective feeling we have of time passing, and in the time of the physicists, there are many subtleties. A famous debate took place in 1922 between the philosopher Henry Bergson and Einstein to discuss these two apparently conflicting notions of time. If anything, the discussion caused the gulf between the sciences and the humanities to grow even more. Perhaps a useful compromise is not to box time into a single definition, but to think of it contextually, as it serves different purposes. Things get even more nebulous when we think about the origin of the universe. The word origin already says it. It is the moment in time when the universe as we know it came to be. Essentially, when time began to tick. How that happened remains a mystery, one that brings forth a whole slew of conceptual difficulties. There is, then, yet another kind of clock, a universal or cosmic clock that started to tick at the Big Bang some 13.8 billion years ago. And if what we know now of the universe and its material contents is any indication, seems poised to keep on going for as long as we can imagine. However, and to make things more interesting, given that what we can say about the distant future depends on what we know of the properties of the universe in the distant future, we can say very little with certainty. Existence, from cosmic to human, is bracketed at both ends by mystery. A world-shattering revelation in a first. Astronomers have observed time ticking in slow motion in the early cosmos, confirming Albert Einstein's century-old ideas about the reality-warping effects of our universe's expansion. By tracking the flickering glows of luminous matter swirling through galaxies when the universe was a mere 1 billion years old, less than a tenth of its present age, two researchers have found that events back then appear to have unfolded at a pace 5 times slower than normal. Their findings were published earlier this month in Nature Astronomy. According to Geraint Lewis, an astrophysicist at the University of Sydney and lead author of the study, for decades, Isaac Newton gave us this vision of a universe where space and time is fixed, and every clock across the universe ticks at exactly the same rate. Then Einstein shattered this vision by proposing that time is actually rubbery and relative. Now we've shown that Einstein was, once again, correct. The Einsteinian concept of time running slower in the early universe arose in the late 1920s as astronomers were discovering cosmic expansion. Galaxies in the sky were found to be flying away from the Milky Way at high speed, swept along by the ceaselessly growing void, and the farther off they were, the faster they flew. This not only meant that the universe was once much smaller and denser, arising in a Big Bang from some compact primordial point, but also that the most distant galaxies visible to us should be receding at close to the speed of light. According to Einstein's special and general theories of relativity, both circumstances alter the flow of time. As light from one of those far distant galaxies travels from the heavier gravitational grip of the deep, dense early cosmos, and across the continuously expanding universe, it must traverse increasingly greater expanses of space to reach Earth. Consequently, time becomes stretched in a phenomenon known as time dilation. A clock running 10 billion years ago would tick at a normal rate to an observer from that time. But from the perspective of someone today, it would appear to be ticking much slower. For Lewis, the work is more than a vindication of Einstein and modern cosmology. It might also prove useful for further exploring the nature of dark energy, the mysterious force thought responsible for a surprising acceleration in the universe's expansion. Standardizing and confirming our models is ultimately a step into the next generation, Lewis says. The goal now is to chart the expansion of the universe in as much detail as possible. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.